Yeah, thank you for everyone attending my presentation. It'll be about designing your multicopter gains from a first principle approach, but taking into account the PX4 architecture. So to give you all a bit of background, our team at Autonosky developed a multicopter capable of carrying a max payload of 30 kgs. But initially we were using a different flight control software and we manually tuned it from the default gains. So when we ported our drones over to PX4, we didn't really want to repeat the same process because manually tuning is time consuming, and especially with a large airframe, even an unstable landing can cause damage and resulting in long lead times before you can actually fly again. So we wanted to have a more informed decision-making behind our decisions regarding the gains. So we wanted to design these gains from a model-based perspective. However, a challenge was incorporating all of the PX4 transformations, normalizations, to ensure once we arrive at the set of gains, it is the same way how PX4 sees the multicopter and controls it. So my presentation will have three parts to it. First, we'll talk about the motor model, which receives a normalized rotational velocity set point and then outputs a normalized rotational velocity. And we're going to lump the ESC and motor together. And then we'll talk about the mixer matrix, which is responsible for transforming the controller outputs to these normalized rotational velocity set points, which get sent to your ESC. And then finally, the controllers within PX4. So as you might know, motors doesn't produce thrust instantaneously. There is some time delay or lag associated when there is a change in set point. And it's quite important that your controllers take these time delays into account. Otherwise, it will lead to vibrations or, in the worst case, instability. So typically, we model the motors either as a first-order impulse response equation or a second-order if you want to accommodate more complex dynamics such as overshoot and oscillation. For this presentation, we'll look at the first-order impulse equation, and you'll see, okay, my mouse is there. Oops. The first order impulse equation is characterized by these two parameters, which is your motor gain, which ensures that your motor reaches its set point at steady state, and then the tau constant, which is responsible for this transient response. So how you typically model these or try to find these two parameters is by placing your motors on a thrust test bench, and then you apply step responses to your motor. So you can see here that initially the motor starts at rest, accelerates to the initial set point, and here you can clearly see that time constant governing the transient response, and then we start pulsing our motor with these step responses. So we'll be looking at modeling our motors in this region because you want to characterize your motors in a region in which it will be actually flying. So if you would model your motor in this region, the model will look quite different. So you want to characterize it in the region where you will be operating it. So how we obtain these two parameters is actually by brute force. By analyzing the step response, you can find good starting point or good starting values for this k and time constant. And then to find the estimated response, you apply like the convolution operation between your guessed impulse response and your normalized rotational velocity set point, which you used in the experiment. And then from there, you then select the best, the best response which fits your experimental data. It's also important that you normalize your experimental data so that your RPM measurements and set points are normalized between 0 and 1. And then here I added the differential equation for this first order impulse equation. It's not of use right now, but we'll come back to it. So yeah, that then ticks the first box, which describes how our motor reacts when it receives a normalized rotational velocity set point. So we can now move on to our mixer matrix. So PX4's rate controllers are three independent controllers, all controlling a single axis and then outputting a single value. So the question is then, how does this single value, which our controller's outputs, gets converted to 4, 6, or how many motors you have? And this is responsible by the mixer matrix, which is within the control allocator module. So how you would then derive these equations is by taking the sum of the forces and the sum of the torques of your vehicle, but specifically looking at the actuators that is responsible for controlling your aircraft. And I've summed these or equated these equations to what I call virtual actuators. So these virtual actuators are just a single variable, which is a summation of all the actuators capable of controlling your aircraft in a single axis. So for example, this is a virtual aileron, and it's just the combination of all of your actuators capable of controlling or producing rolling torques on your aircraft. So we can then take the sum of the forces, and with our multicopters, the motors are typically mounted only in the z-axis. So the sum of the forces in x and y is equal to 0, and then we can then substitute the motor equation into our sum of the forces. It's very important that your rotational velocities must be normalized. This is just how PX4 models the drone within the software. And this will result that these motor constants is going to be your maximum thrust that your motors can produce. And then we just rewrite it in this matrix form. We then look at the sum of the torques, and it's just the thrust that your motors produces multiplied by its position relative to the origin in the specific axis. And these positional variables are then the geometric parameters that you type in Q ground control in the actuator tab to set up your mixer matrix, actually. So we can then combine these two matrices, the force and the thrust, and then we obtain this equation over here, which describes the relationship between our rotational velocities of our motors to the thrust and torques which gets produced in the various directions. However, this mixer matrix, this is not the mixer matrix. This matrix is known as the control effectiveness matrix within PX4. However, this is not in the right form that we desire. So to remind you, our controllers outputs these torque and thrust set points, which is then as input to our mixer matrix, mixer matrix, whereas in this equation here, we have our input as the normalized rotational velocities of our motors. So we need to invert this equation. So what PX4 then does is it calculates this inverse matrix of the control effectiveness matrix, which is then known as your mixer matrix, and it has this property of when you multiply it with each other, you roughly equal to 1. So we can then multiply this inverse matrix on both sides, realize that roughly equals to 1, and then we obtain the form that we want. So as input, we have our sum of the torques and forces, and then left multiply with the mixer matrix, we obtain the normalized rotational velocities that our motors need to reach to produce these torques and thrust. So PX4 then goes further and normalizes this mixer matrix. I won't be going into this, but all further mentions of the mixer matrix refers to this normalized mixer matrix. That then ticks the second block where it describes the relation or this transformation between what the controller's outputs and the rotational velocity of our motors. So we can now look at these controllers of PX4. So to to design controllers from a model-based perspective, you need to apply Newton's second law to your motor. So this is the forces of the sum of the forces equaling to the mass times acceleration, and then the same with the sum of the torques. And it'll become more clearer a bit later on. But PX4 makes use of a cascading control architecture where each controller is built on top of each other, and where your rate controller is responsible for controlling the fastest dynamics of your system. So I'll starting at your sum of the torques, and then we'll build out from there. So when we look at the sum of the torques, we see that it is the torques that each of our motors produces. And then a term which I've already neglected here is the effects of gravity. So when designing linear controllers, you assume, or you need to define an operating point around which you're going to design these controllers. Typically you would design these controllers around hover, so then the effects of gravity is neglected. And then we'll then substitute our mixer matrix into these each of these motor rotational velocities, which will then simplify the equation quite significantly. And so this is the equation after we have do the simplification, and I'll describe each of these terms on the next slide. And then you already see it now. I'm using my virtual elevator here, which is just the sum of the forces in the torque or in the y-axis. And now I'm going to substitute our motor model into this differential equation. And you might be asking, we've derived our physical motors time domain behavior. Why am I using these virtual elevators? And it's because the mixer matrix is responsible for converting between our physical motors and these virtual actuators. So if our physical motors has a certain time domain behavior, our virtual actuators, or the sum of the forces or sum of the torques, will have the same. So we can then substitute it in, and it results in this equation, and then you would then apply the Laplace transform to obtain this transfer function where you can then start designing your controllers. So this is then your model for your multicopter in the pitching axis, which is defined by all of these key parameters that we have mentioned. So your motor time constant, the moment of inertia, your moment arm from that your motor is from the center of gravity, the motor thrust constant, that motor gain that is present in your motor equation. And this mixer matrix coefficient is a coefficient once you substitute it in, this coefficient arises, and then the number of motors contributing in the pitch axis. So now that we have it in this form, we can actually start designing controllers, which is producing this virtual elevator set point. And we can design it in such a way that will manipulate our model of our multicopter in the way that we would want. So luckily, PX4 already defines these controllers for us. We don't need to figure that out as well. And PX4 makes use of an alternative PID controller, but for small angle approximations and the linear analysis, we'll just be making use of your classical controller. And then we can place it into this controller block diagram where our controller is producing this virtual elevator set point, and our model of our multicopter is receiving it, so over here, and then it produces the angular velocity based on this model. And then we have the feedback loop where our controller reacts on the error. So you can now apply any controller technique that you want to start designing for these PI and D controllers, but I'll be making use of a method known as the root locus. So I won't be going into the details of how to design these gains based on this root locus, but you can now start selecting these PID gains by looking at your root locus, and it'll then produce two different responses. So you'll see this bottom one is much faster than the bottom to the top one. And then once you're now happy with your response that you have, The next step is then to compare this closed-loop response bandwidth to your motor's bandwidth. And you want to ensure that these two are well separated. Otherwise, the controllers will actually, in a sense, start fighting with each other because your pitch rate control system is now producing set points too fast for the motor that the motor can actually react to. So you need to ensure that there's enough separation between these two. And then once you're happy managing the balance between a fast response and this separation, you can move on to your angle controllers. So the angle controllers of PX4 produces the angle rate set points. So in this controller block diagram, the angle controllers are actually controlling the closed loop of your angle rate system. However, PX4's angle controllers are in quaternion based, so we need to account for that because this controller block diagram is in Euler angles. So since we are designing linear controllers, we can apply, again, small angle approximation. And this will result in that we'll see that the second quaternion's element is responsible to half of the pitching rotation. And then we can apply this transformation into our controller block diagram, which will then transform our controller block diagram into a quaternion base. So here's the closed loop block diagram for our pitch rate system. We then incorporate this transformation to bring it into quaternions, and then we can just multiply these three blocks with each other to obtain the model for the quaternion controller. And now we just repeat the process of designing this proportional gain in the root locus, and then designing it to the point that you're happy with your closed loop pitch response. And again, you need to then ensure that there is enough separation between your pitch rate closed loop system and your pitching closed loop system. Otherwise, again, these two will start fighting between each other. So once you're done with that, we move on to the velocity controllers. And now this cascading control architecture of PX4 is becoming very clear, where each controller is being built on top of the other, and each is seeing the closed loop system of the inner one. So PX4's velocity controllers are written in the inertial frame, and its outputs is acceleration. It's an unnormalized acceleration, which then gets converted to a normalized thrust set point, and then finally to a quaternion set point. So we again need to accommodate these conversions to ensure that once we design our PID gains, it is the same way how PX4 sees and controls our drone. So how we do this is then we describe a scenario where our drone is maintaining altitude and flying in a north direction. We can then apply, again, Newton's law, and then apply small angle approximation, and we'll see the thrust that our motors needs to produce is roughly the mass of our drone. And then we do the same in a north direction, and after simplifications, we find the relationship between our acceleration set point and the quaternion set point. So the last thing now is then to find the relationship between acceleration and force. So we can say that our normalized force set point is multiplied by the maximum thrust that our multicopter can produce, and this will equal the unnormalized thrust set point. So this Tmax will typically be, if you have 4 motors and they both produce 10 kgs of maximum thrust, this will then be 40 kgs. And then the second equation is just Newton's law, and we can then equate these to each other, and then we find the relationship between our normalized force set point and our acceleration set point. We then substitute these conversions into our controller block diagram, and then we can simplify, and then we find the model on which our velocity controllers will control on. And then we just apply the same procedure where we design the velocity controllers in whatever control technique you want. But here I've used the root locus method, where you select these PID gains based on your root locus and then find the corresponding closed loop response for that system. So and then again making sure that there's enough separation between these controllers. So for the position controller, it's exactly the same, where your position controller is then operating on the closed loop closed loop system of your velocity controller. And there's no transformation needed between your velocity and your position, just with the use of this 1/s operator in the Laplace transform. So just want some practical results from this approach. So after applying this controller process, our maiden flight with our hexacopter was stable. This technique is not to arrive at the set of gains where you have a finely tuned aircraft, but rather to have an informed process of where to place your controller gains and to be at the point where you can actually start doing your fine tuning. So it reduced our number of flights to arrive at our finely tuned aircraft by 50%. And then during the first maiden flight, there was some vibrations evident in our airframe. So we needed to drop our rate controllers by 10 to 20%. Our angular controllers were unchanged. However, the closed loop response was much more damped than what our linear system predicted. So that was actually an increase in performance. And then for the velocity controllers, we just had to adjust the proportional and integral terms to ensure that we have the transient response that we want and enough disturbance rejection. Another benefit of this process is you can now start placing your low pass filters and your notch filters into these controller block diagrams, and then you can actually see how much it is affecting your closed loop response system. But I didn't show this now. So this then ticks all of the boxes from your motor model, mixer matrix, and then designing these controllers within the PX4 architecture. And just a reference to a master thesis that also followed the same procedure if you want to have a look at it. So thank you for listening to my presentation. I really do hope it will bring benefit to the community for those who want to have a deeper dive into designing these controllers from a first principle. Thank you.
Hello. Hello. All right. We got time for a few questions. Raise hands here.
Yeah, you mentioned you wanted enough separation between the controllers. Do you have any rule of thumb of how much is enough?
So we use a rule of thumb between, for the faster closed loop system or the slower closed loop system needs to be cutoff frequency needs to be 3 to 5 times slower. Yeah, so depending on how confident you are in your model, you can then, if you want to be more conservative, you can make it 5 and then go test fly. And if you see, you're not getting, there's not any vibrations issues, you can then bring it up. Yeah.
Any more questions? Food coma? Yeah? All right. Thank you, Henry.
Cool, thank you.